OK。OK， 那我们开始吧。上次我们介绍了解空间 tangent place， 解空间解向量场，然后解从所以我们复习一下，解空间去向量空间，这个 P 我们有这个解空间的 basis is given by 这样。然后切从 Tm is the 切从是解空间的并集。At each point you have a 解空间 and then we collect all the tangent space smoothly. So 切从本身是2m 为流行，所以dimensional manifold 这边是dimensional manifold， 然后我们可以这是 projection。我们会考虑结带，我不知道怎么是结带。section， section 怎么写的？我不知道。接待。section 怎么写的？结带不是结带，截面，我们考虑截面。截面。So at each point, you assign some on the fiber like so you have a point P, you have a TPM, and you pick point S of P, and it smoothly moves like this. 这个定义向量场 vector field。这个 section 满足pi S is equal to identity of M， 满足这个性质。 practically, 我们 schematically 我们会画这样的三面墙。三面墙。然后 x is given by sum of x. Locally, so if you have the some open covering, so the open covering, then one can write down the challenge with this basis. Okay. So this challenge the challenge function 我们写的是 prop x of n。这个是光滑映射 c infinity of n 到 c infinity of n， so 这是光滑映射的空间到光滑映射的空间。So s is equal to x of n. On the other hand, so this 这空间是的光滑映射，从 c infinity of n 到 然后我们学过这个三人称周围的性质linearity， 然后 Leibniz rule， 然后三人称代数结构 So this satisfies the, for instance, the linearity, so x, y, and then x plus y is also in the vector field, and the x given like this is also, so this the 括号 is also vector. So when you write down from a Chinese practice, 括号 the bracket. Okay. And then they satisfy some like some 性质。So the Jacobian C antisymmetric and bilinearity。然后最后我们考虑这个integral half and the float。So 就是积分。曲线 and then here. So 积分曲线是 the 积分曲线是the curve which satisfies the following equation. So given the 相链长 ，so 给定相链长 x， 我们考虑这个积分曲线。比如说，如果 given this 相链长point P and then we can just consider the integral curve whose derivative here exactly match with the x of p. So exactly this curve, the speed of this curve is given is equal to this vector challenge. And then if you write down the local coordinate, for instance, local coordinate 逐步坐标，所以我们可以capital X， 我们可以写这样的。And then there's always there's a theorem saying that given this is ODE, this is ordinary differential equation. Given the ordinary ODE, there's a unique solution of this capital. So this is capital S. For sufficiently small 十分 small t. There's a unique solution for sufficiently small t. Okay, so this is small x. Small x. Sufficiently small. Given the point P, x of I of t, we can have small x over t. The solution for sufficiently small t. The unique solution, so that you can always consider such a flow, not flow. So there's a 积分曲面不好意思，积分曲线，积分曲线，然后如果这个积分曲线对有所有的 t， 如果 t for any t xi or t or this gamma of t, there exists such a solution. Then this vector field is complete. X is 北圈位 is 往倍的 complete 是往倍的往倍。So this can be always done for compact, as I mentioned, compact manifold, for closed manifold. For instance, the last time, so we considered the rotation. For instance, 旋转流. For instance, last time, was S2. So X1 x3 this way, and then 绕 x3 轴的旋转去 something like that. And then vector field is something like that, always become like this way. The last time, as I mentioned. So x is equal to more like x1 delta of x2. So this is the vector field. Actually, in this case, this gamma of t is called flow. In this case, flow will be given by this cos t sin t minus sin t. Like this. This is the flow of the S2. Flow of S2. And to satisfy so this flow will map like a phi of t, so m to m, cross multiply m. Okay, so let's map p to gamma p of t. You just map to, so you start point P, and if by flow you just map to this gamma p of t. That's the okay, that's the case. Sorry, my notation is different. And then, so this satisfies the following condition. This satisfies the following condition. Okay. Any question at this moment? So this is called flow. Or maybe, yeah, anyway, so that's the. So this sometimes it's called a one parameter family. This is called a family of differential. So this flow is sometimes called one parameter family. One parameter is this t. This t of diffeomorphism. Always this is called diffeomorphism. Okay. Okay. Okay, one parameter family, one parameter group. Okay, so that's the case. And as I mentioned last time, so 所有的向量场，不是所有的向量场都完备。It's not complete. For instance, you just consider the R2. Okay. R2, or maybe the simplest example is something like this one. R, and then just get rid of point. You just have R, and then you just remove origin. Okay. And vector field is something like that. It's given by just delta x, for instance. But you start with point like say -3, and then with this flow, after t is equal to 3, you just stop here. You cannot move forward. Okay, you cannot move forward. So therefore, not all the t. This is how to say mu is not defined. That's mu. Okay. So another concept we'll consider is this Differential orientation. So Differential is always okay. So you can have a point P. So point P, you can have the two bases. So you can have a point P, you can have two bases. EI and then E tilde I, the basis, and they are related. So basis of this Cotangent,然后就是这个坐标变化I something like Bij and Ej tilde. If this Bij, determinant of Bij is positive, if it is positive, then E and E tilde has it's called same orientation. If determinant is positive. Okay? But if they don't have if it is negative, they don't have a opposite orientation. The two bases have a different orientation. Okay? And if you can always assign such orientation smoothly, then manifold is called oriented. 有定向。Sorry, oriental. So 就是可定向。Sphere is one of the example 可定向的例子，但是不可定向的例子是 famously maybe star. Okay, so you just is there something? Unfortunately, no. You just have a strip, but when you just do not how to say the strip, you just how to say glue them together in the opposite way. Okay? So therefore, if you have you start with and then you just come in here, you have like this way, E1 and E2, then you have E1 and then E2. So you just move this frame to go around this circle and come back. You just have E2 directions become opposite. Okay. E2 directions are opposite. So therefore, this means that it's not the 可定向. So 不. So maybe strip is 不可定向. That's the example. Any question at this moment? 这个是不可定向的例子。然后另外一个例子是 RP2，也是不可定向的例子。RP2 is again okay. So RP2 is defined by its opposite point. So this X opposite point. So therefore, so this point is identify this point. This point. And then, for instance, if you consider the frame, just consider, okay, maybe the opposite example is bad. So you just consider this one, and this point, and this one. If you consider this one, and then this one, and then if you set like this way, this is, in fact, you should go to the opposite way. So it's like this way. It's downwards. Okay. So this direction of the vector field is the opposite side should be downside. So to south, because I mean it's just this north is identified south, right? There's a south by this identification. Okay. So therefore, if you move this frame along this equator, you will get a different orientation. Okay. So you cannot have a consistent orientation for RP2. Okay. 这个是另外一个的不可定向的例子。有没有问题？如果没有的话，我们我们考虑那个预且空间。So Cotangent is the 向量空间，然后线性代数知道对于任何向量空间都有这个对比向量空间。OK， 这个 dual vector space. Given the vector space, there is always dual vector space one can consider, which map V to R. So one can always consider such a space. So therefore, for instance, that's the case. So R for I just R, Xi is a P. So likewise, this dual space is TPM to R. So given the XP, EFP is equal to XP of F. So F is now, so here, F is the some function. It's 光滑映射 F is F 是光滑映射。然后就对于向量空间成为与虚空这样Cotangent。Cotangent. So here, given the basis, of the tangent space, we create构成有机空间的基地是 dx 有 dx the basis 基地有机空间的基地是 dx1 就 dx2。The natural pairing, so 自然配对给出 dxi, dxj without the light. You can just have the natural pairing. So here you can also have a natural pairing. Oh, sorry, I think the most natural way is writing like this. Point P, maybe point P, point P, so切从是切从是这空间的定值。Likewise, the U 切从 Cotangent bundle 是有机空间的定值 collection， 这个 collection， 我们 consider 有机空间。Okay, so that's the case, and this is solved. So 如果计算有机从本身是那个 2n-way 流行 2n-way 流行 T star m 就 这个是 projection，and then 我们会考虑这个截面 section。那这个 section 成为光缝 ，is called 光缝 section of 光缝。So 切缝的截面是向量长，但是预切缝的截面是弯形式，弯形式，一形式 ，and the often people write down like this. Okay. So vector field is like this way. We write it like this way, but the space of one form is the capital omega one. Just like okay. So given that one can define like this way, like this. So the EMF is a map from and then, so recall that this X is the vector field. So dF is a map from 光滑印象从this space of vector field to the smooth function. And recall that the pairing between X and the X to the F will give you another smooth function. So therefore, this will give you the action of the map from of dF from vector field to the smooth function. That's that. Okay, so those are the dual of the 对于解光针。So now we can consider the following. So given the manifold M and N, and then the smooth map, 流行两个流行 M and N, and then 我们考虑光短映射。Then TPM is mapped to T of FE of N. Okay. Then we can consider so-called push forward. Push tuition of S star of TPM to TFOP N. This is N. In such a way that the X is mapped to F star of X. And then, so as you recall, the F star of X acts on the function on N. Okay? So therefore, so F star given the G, like this. Yeah, for instance, if you have an XP, I mean, you can put the P here, We have XP vector, tangent vector here is mapped to be like this way. And maybe I should use the color. XP. So this is tangent vector. Is mapped to its push forward to the F star XP. It's just push forward to each hand. So this one, so this is F, and another map is G to R. Okay. So composition of F and G will give you the map from M to R. Okay. M to R. So therefore, tangent vector can act on the function on M. It's a composition of F and G is a function of the M. So therefore, the tangent vector can act on. That's how you define this push forward. On the other hand, so this one form is the dual of this one. In this case, we have a pullback.拉回 pullback. F star is TFOP star N to G star. So you just consider the cotangent space of FOP and the pullback to the cotangent space of the manifold N. Okay. So how do we find that? So if you have omega FOP is mapped to F star omega FOP, then we can just define like this way. Any function F star of the X P is you can have a natural pairing FOP. You can have natural pairing. It's just F star. Like this. So you can consider omega omega f of p. And if you consider omega f of p in this point, you can have a natural pairing between cotangent space to tangent space. Okay, natural pairing. Because it's a vector space. 这种配对，我们有这种配对，对这个右切空间和切空间 natural pair because that's how you define the dual space. Okay? This is natural pair. Natural pair. Okay. At this point, you can have a push forward vector field and the original one form. On the other hand, here you have pullback of the one form with the tangent vector with the parent. Okay. You can have a parent between. So this one is F star. Omega F. Any questions? Okay. So 这个且空间under this 光滑映射像且空间有对称 from home. On the other hand, 这个 one form or 右且空间 have this 拉回。It's the opposite way of moving. Any question at this moment? Any question at this moment? Okay. So another thing which is important for push forward is F star. It's a map, linear map from S. So linear map is the 线性印象 Is it okay? 线性印象 linear map is TPM 到 TF of P linear map. So this is a linear 线性 linear map. Huh? Isn't something wrong? Okay. So if this is the onto, this is surjective. Surjective is 盲秀. It is surjective. Okay. And the rank of, you can consider rank of a star is equal to dimension of n. Then F is called at point P. At the point P is regular. Regular is gentle at point P. At point P. Okay. At point P. So for instance, if you consider the following thing, so this S2 to R, okay, S2 to R, if you consider the map from S2 to R is just a, you just consider project to X3. So you have a X1, X2. Okay. And if you put the point P around here, okay, so then definitely, so if you have considered the tangent space around here, tangent space, then this kind of vector, so this xp is mapped to just mapped to this point, okay? And the push forward of this vector field of the tangent vector is something like this one. Okay. Tangent vector is a push forward of tangent vector. So therefore, it's really onto. Okay. On the other hand, if you look at the north pole, tangent vector is something like this one. Okay. Therefore, a tangent space is like this way. If you consider tangent space x p north pole here, this is mapped to just point here. Okay. So it's tangent to this orthogonal to x3 axis. Okay. X3 axis is orthogonal. So therefore, whatever vector you have, you just map to this point here. Okay. You just map to this point. There is no x3 direction. Okay. So therefore, this map from tangent, let's say north pole, and north pole of S2 to this point, to this T of R, say 1. So the unit circle R, this one is not the rank is not 1. The rank is 0. Because all the tangent vector is mapped to the 0 here. So rank is not 1. Okay, you know rank, right? Rank of the linear map. I hope it's okay. I mean, it's just a n by n matrix dimension. So m by n matrix. Okay. Whatever, m by n matrix, and you have the it's called minor in n by n minor should have the inverse. That is the meaning of rank n. Okay. Inverse. But on the other hand, here just all the map is 0. So therefore rank is no longer 1. So therefore it's not a regular point. In that case, it's called critical point. So otherwise, P is called critical point. Of F. So critical point is E. It's called 临界点。临界点。所以，如果我们考虑这样的 map， 就是 height map is called height map。北距和南距是临界点，是临界点，对。OK， 北极北极 and 南极是临界的，南极是临界的。Okay. And this is so very important theorem. 非常重要的定理。Third. So 这个临界点的光滑映射的临界点有 Rubik measure 0。Critical point. A set of measure 0. This means that the critical points are very special. Okay. Critical points are very special. Measure 0 means the inside R is just a line or like a inside R3. Inside R3 it's like a line or how to say surface or surface. It doesn't have a body. It doesn't have a body. That's the meaning of measure 0. So this means that the 临界点是特别的。So it's not like a common. It's not like a spread all over the map. Okay. Another thing is we can consider is that the immersion 这个怎么说呢？进入。Another thing is the if is injected. 这个是单射。For any特殊。Yeah. Oh yeah, I didn't write that. So I didn't write that. I should write that. So the set of critical points are very special. So it's not like, for instance, in this map, so this south pole and only like a north pole and south pole are these critical point, and the other places are all regular. Okay? The other point. It's just that, yeah. It's just, so this means that the north pole and south pole critical point are very special. 非常特殊，非常特殊，临界点是非常特殊的。Now, if you consider this, the map is always injected down, then f of f is called immersion. immersion， 所以这个是进入 ，it's called 进入。Moreover, if F is immersion, furthermore, M to F of M is homeomorphism to 东淮，不是东淮，同胚 homeomorphism 同胚 then F is called M. I think embedding. This is 渗入嵌入，it's called 嵌入，这个是同胚。I'll give you one example. I think I can erase you. So 嵌入的那请给我嵌入的例子。请给我嵌入的例子，一个例子。Okay, so this is 这个是嵌入的一个例子。那 for instance, x to x b， 所以 just r。the concept line this is embedded. That's true. Another example is Sn is inside Sm, where n is less than m. The x is mapped to x0. The for instance here, inside S2 one can embed S1. One can embed S1. Okay, one can embed S1. Is it okay? 这个也是嵌入的一个例子。Another 另外一个的例子是T2. But there's a lot of ways to do that. One way is something like this way. So if you write this red. Another way to embed is something like this way. This is something like this one. Oh, there are lots of ways to embed that. For instance, if you write down something covering space of this, so always this part is identified, and always this part is identified like this way. That's called covering space. It's called 覆盖. Is it 覆盖 or 覆垫? 铺垫. And then we can consider the following thing. 铺垫. So every point are identified. All the lattice points are identified. So therefore, we can consider this kind of line. Then, so here, this one has a 3 times in this direction and 2 times in this direction. And at the end of the day, so it becomes like this way. Path is something like this. It becomes like this. Inside the torus. Inside the torus. It's something like this. It becomes like this. Let's do a triple. 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 So this kind of embedding can be done, but if the slope is rational. If slope of this line is rational, at the end of the day, it just hits to some lattice. It hits some lattice point. Okay. Slope is rational, so n over m. N and m are co-prime. Okay. So then, if you just go from m times to here and n lattice point, and it just hits to the lattice point there. So therefore, you can close this one. However, if this slope is irrational, rational is 有例数 of the same as 有例数 same as Japanese. Okay. Irrational is 非有例数 无例数 If it is 无例数, it will never hit the lattice point. Okay? So then, what's going to happen is that so it never hits the lattice point. So therefore, this irrational line, like whatever irrational line, is that it becomes like this. It's really dense. Densely populate on all the torus. Because it never hits the point. Therefore, so this torus, each torus, and they just go to the different point and so on. So they just never come back. So therefore, it becomes like this. But then S1. Sorry, no, S1. This R is mapped to this T2 here. And you can take the small neighborhood, then it definitely hits like this R. You have an R. And a point P, you can take a point here. Yeah. The open neighborhood is something like this one. So this segment, open segment, we try to map to here. But if you take an open neighborhood of the torus, it always have another. You just take another point too. Because I mean, it just you cannot separate the next point. You understand what I mean? If you take open, if it is irrational, if you take this point, but if you take this point sufficiently small, it never hits any place in its green line. However, since it's irrational, it becomes open dense. Become like this way. So therefore, if you put point here and take open neighborhood, it's inevitably includes somewhere else in R. So therefore, this open set is not mapped to homomorphic to the open set in the image. So therefore, this condition is not satisfied. So therefore, this irrational embedding from R to T2 is called immersion. Immersion is 进入. This is 进入. But not 嵌入. So this is an example. Any question? So let's start. It's regular. For any P of n, that is called submargin. Submargin,请告诉 submargin 的中文翻译。樱木。I don't know 中文怎么说？那我问多包 ，How do you say submersion in Chinese?
Submerge 对应的中文是 submerge 进入 submerge 数学里一般写成 submerge 二次进入或亚进入，更标准常用的数学术语。
Submersion in Chinese.
Submersion 在数学微分拓扑、微分几何里的标准中文术语是淹没，完整说法淹没映射。例句 A submersion map 一个淹没映射，需要我顺便帮你区分它和 immersion 进入的中文。
谢谢。淹没。
不客气，有其他数学英文术语需要翻译，随时问我。
Is it 淹没？我。It's not made. Okay, this is called immo. Is it like this? Y-A-N. Y-A-N? Y-A-N. Yeah, yemmo. M-O. Yemmo. Wow. Okay, thank you very much. Yemmo. That's a very good. It's very good practice for my good lesson for my Chinese lesson. Okay, thank you very much. It's called submersion. Okay, and then given a cube, so given a cube, the inverse of cube is a manifold. A manifold of codimension. Dimension. Okay. So for instance, if you consider that M cross M is mapped to this projection map. So this is submersion. For instance, if you consider torus, or this is bad. And you can consider the following S1, torus to S1. S1. So you just identify this point and this point. Okay. So you just identify top and bottom point, you get the S1. And then given a point here, I think yeah, given a point here, and then so this is Q here. So it's just projection. And then pre-image of Q is this one. This is F inverse of Q. F inverse. And codimension is literally this direction. Then transfers to this direction. Transfers to this pre-image. It's called codimension. It's called codimension. 这个是鱼尾 codimension is 鱼尾 is dimension n. So in this case, one dimension. Okay, I think it's a good place to stop to take a break. Okay, let's take a break. I prefer to stay right after P. That's fine.
Yeah, because after I mean.
Yeah, that I agree.
I'm confused about this.
That I agree. That I agree. I mean, the usual notation is just put the P here. Yeah. Just too late.
Okay. I almost went away. We're only on 2 for this.
Oh,
only 2.
Is it only 2?
Yes, only 2.
It's not the 煎蛋的蛋.
It's the same kind of different Chinese.
Oh, I see. Okay, I didn't know.
I'm going to introduce.
You learn Japanese?
Yeah. I'm always confused about this.
Okay.
Actually, we can also read those. Some different we can also read.
Yeah. No problem. But when you write, you have to be careful. Okay.哦，这门课是对我的中文非常非常有用，我非常好的练习机会。呀，中文很难呀，特别是发音，然后我已经老了，所以我的脑子不能not flexible enough to 适应很多词汇啊，适应很多词汇啊，语法啊。如果我学习新的词汇，马上就忘了。 所以我的中文不提高。唉。微分形式，考虑钢铁形式。烟幕。
太理解，你说的烟幕。
烟幕映射。It's not. Why is it called local May? I see. 线性射映，线性射映。线性映射，线性映射。就向量空间或者线性空间都可以吗？都可以。Linear space. Okay. So which one is often used? 向量空间 Both are often.
You always use extension.
Linear. Vector. I think vector space is more often used, frequently used. That's my.
Sometimes we are dealing with the more general.
I see. Yeah. 有限微度，有限维度。有限为线性空间，无限为线性空间，使线性空间负线性空间，子空间。How to say quotient space in Chinese? 相
Quotient space 在数学里的标准中文是
相空间，OK. Same as Japanese. 相空间。
需要我顺便给你举个简单例子吗？
但是现在这个人工智能真的方便，在上课的时候也可以用。I forgot to record. I forgot to record lecture. 那我们继续吗？那我们已经引入了这个一形式 form， 而且呢，我们考虑更高阶的形式所引入就是外接，所谓微分形式，所以 differential form。Sorry, so this is I course. I just checked. Okay, so 高阶的考虑更高阶的形式要引入外接或斜接exterior product。So this is the wedge product. So wedge product or exterior product, whichever is okay. So this mark is product. Okay. So of course, if I dxi with dxi is equal to 0， 特别的是这个，然后。We can consider the wedge product. Okay. Like this way, or maybe we can put the P here. Or of course, you can put the P here if we consider tangent space. And this one, so for instance, you show with TP star M inside of omega is X is the map of TPM plus TPM to R. Okay, bye. Is it okay? So this is the multilinear map, K-linear map. So 这个线性映射。Okay, and satisfy the following. Okay. So here all are tangent vector. Like this. In particular, sorry, and also this sigma is the element in the symmetric group. Sigma is permutation group. That's permutation. So, in particular, so this when k equal to 0, k equal to 0 case is just a function. It's just a function. Oh, sorry. I think it's better not to. Okay, it's just a sorry. Okay. In particular, so omega can be written like this way. Equation. So each omega I are the one form. Okay. One form. Also one. Okay. Okay, and then omega 1, which omega, so if you apply this rule, so we can just consider the following thing. 1 over k prime determinant of omega 1 x1 omega 2 x1 omega k x1 and here omega 2 x1 omega 1 x2 omega 1 xk omega what was that? K xk. You just take a determinant of this. That's a rule of this taking exterior product. And of course, xi is a tangent vector. And like this. So that's the. And more generally, if you have the omega, which omega is k form, and the A is the L form, the omega which L, A is the like this. So if you use the permutation, one can just have the pairing between first k tangent vector and the other L tangent vector, and then just use a permutation and add them up. And then all the differential become consistent. And likewise, if you like we define the define the 定义语切空间的时候，我们并举 cotangent 并举each point to the cotangent space. So likewise, we can consider the following thing. Like this way. So you just consider collection of the all point of the all the point, and then consider the consider the collection. And in this case, you need to be careful about the collection. So transition function. Transition function is transition function 转变汉学吗？Transition function is what? How do you say? 转变汉学。Anyway, so given the local coordinate, so manifold, and you have given so u x1 one is u x1 dot xm, and the other is v dot y1 dot ym. You need to be careful about how the bases are transformed. So in this basis, of course the bases change. Bases are given by like this way. On the other hand, in this basis are given by like this way. And how is it transformed? The question is. Like this way, and then consider the following thing. And here, this is Jacobian. Okay, Jacobian. So this is essentially given by like this way, x1. It's really tedious to write down. J1 is and dot, and then x. Sorry. Okay. This is the y jk. And then, so the other is just permutation of the indices of J1 and J. So each element, Jacobian, each element is like this way. And then the other element will come from the permutation. Any question this moment? So this is again the bundle.在哪里？这个也是向量this is called 向量场，向量层。vector OK， 请告诉我这个维度，它的维度是什么？维度是什么？请告诉我它的维度。那这个是的向量空间，这个向量空间的维度是什么？It should depend on K. OK， 这个向量空间的基底是这个，基底是这个，所以 the dimension of this one dimension is equal to n choose k binomial. Okay. And choose K. Or, I mean, if you write the C, I mean, in China, most likely it's written like this way, opposite, alpha.
It is on the right up.
Like this way? Like this way? Okay. Anyway, so this is the dimension of fiber. So I that's why I don't like this notation. This notation I prefer. So therefore, this is fiber. And then, as I mentioned, so the vector bundle is the M is the base, and then 相当层 and how does that fiber in Chinese? 纤维是n choose k 的 dimension 维度 so okay. So therefore, the dimension is like this one. Each fiber is the 纤维有 n choose k 的 dimension 维度，然后 the base manifold is the maybe 几六型是有 n 维，所以我们加 n choose k 加 m， 这个是对，这个是它们的维度 ，OK， 它的维度。那如果有向量层，我们可以考虑截面。如果我们考虑截面，so the space of section，截面的空间，我们是这样的 gamma capital gamma， 这个是什么？切从的截面是什么？向量场。U 切从的截面是什么？光孔。我们是这样，omega 1。那So this is the space of K form. K form K 形式的空间，空是 chapter omega K。So 特别是 omega 0 of m is the m 流行上的汉数。So 这个是 differential， so 微分 ，so 这个是微分 ，K 形式。微分形式。如果我们用这个G D 这个 G D omega 这个微分 K 形式。这个是你 function on U， 这是开腹地的function 的函数，跟 I1 保利。那我们已经学到，就是这个 omega of m 是光滑映射从向量场到函数。这个是 omega 1。那 omega k 的话，在这里一样，这个是这个是U 切空的外积，所以我们考虑 kth power of the cotangent space tangent space 一样的，所以我们考虑 kth power of the 向量场到 C infinity。 这个是K， 线性映射，线性映射。这个空间的特别的性质是它们有 external 这个是 external derivatives y 分 微 y 微分 y 微分y 微分有满足以下三条性质。第一是作用函数 f of x is x of f。第二是 d square is equal to 0。第三是 Leibniz rule。d omega A is d omega A plus minus 1 to k omega A dA。So of course this is the omega k and this is omega A。So 这个 y 微分是这三条性质。So 如果我比如说，如果我们用这个逐步坐标用的表示的话，so d omega 是这样的 I1 和 IK df I1 IK x wedge dx I1 wedge dx by k， 这样我们可以这样写。特别是这个是到 f 到 x say I k plus 1 dx I k plus 1 sum of I k plus 1这样。所以我们有dx k plus 1 y 值y 值的这个是汪形式。数学家不喜欢这样的 用逐步坐标的表示。数学家Mathematics do not like this local coordinate using the presentation. So more like a general way of like without relying on local coordinate. So this is physicist way of understanding external derivative. So mathematician is often considered the following. Like this. So oh yeah. So this hat means you omit the vector field. So therefore, omega is the omega 是 k 形式，要这个bracket inside 要 this k k 向量长，所以 so you have to omit one 除掉一个 vector field 向量长，这里一个例。括号，里括号，但是我们去掉两个向量长，所以 in total 这个 k 向量长。So this is coordinate free. So this is local coordinate free way of defining the external derivative, and they're equivalent. And this equivalence is kind of like homework. So it shows homework. And then second form. Any question? 你有什么问题吗？ So here, xi any vector field. Again, so 推前往后拉回 pull back and push forward. So given the map from given the 光滑映射 m 到 n， 我们考虑推前去 xm to the vector field is push forward. On the other hand, pullback is the one form. The 拉回 one, sorry, and so搞这形式也一样的行为，一样的性质。So if upper star is omega kn 到 omega kn。决定这个光滑映射，我们可以将 n 项的 k 缝 n 项的 k 缝k 形式拉回到 m 项的 k 形式。它的性质是这样的。那如果我是这样的话 ，xi 是 m 项的向量场，或者 n 项的向量场。你说 m 或者 n， so xi is in the vector field on m, and omega is n 项的 k 形式。这个我们可以推强 xi 到 n 项到 n， 所以我们可以配分这样。Listen， 拉回的形质是这个形质，光是线性。第二是与世界相容。OK， 然后如果我们考虑的话，然后最后一个最重要的，所以这个是与外微分与外微分交换。外微分交换。比如说 ，so omega kn is 拉回到 omega km， 但是第一外分到 omega k plus 1 and f star omega k plus 1 m and D。这个路线和另一个的路线是一样的，这个是交换性。这个微分信息，微分形式，不好意思，我的，微分形式，对，不好意思，微分形式有好多有趣的operation 作用。一个是一个是integral product。Integral product is内乘内值。So given that x is a 下链乘 Ix。你曾觉得对，这个是 K 形式 ，K 作用 K minus one 上链乘是 up to factor with So, 其他的作用是力微分，以微分。The derivative is defined as follows. So 这个 phi t 是什么 ？phi t x is the x 是相链场，相链场给我们一个流，我 one parameter group of dependent operators. To phi t is the flow. Flow流 generated by x 的流。但这个是同配，所以我们能考虑这个拉回。外围分的对，外围分的拉回 ，and then take derivative by taking t equals 0. This is called Lie bracket. And then Lie bracket can satisfy the following thing.这个是欧米伽作用 K 下面场，这量是的一个函数 m 下的函数 ，x 下面场可以作用函数，所以。This is the so this is everything the functions on M. So this is the case. In particular, we can do the similar thing. So Lie bracket. So here this is one pullback of the constant of K's form. But we can do the same thing for vector field. Then t equals to 0 by minus t, and then push forward of y minus y of t. So we can push forward y by flow generated by x, and take derivative of some vector. That will give you in fact Lie bracket. What else? 有没有问题吗 ？And then this 内积和力微分有好多这些共识。If you open the Morita's book, Morita, like a geometry differential form, there are lots of identity. Oh, by the way, so I erased by the way, so I forgot to mention third theorem, third degree, 有很好的说明，在 Milner's book. Milner's is differential geometry from the viewpoint of topology from the viewpoint of differential geometry. That one has the beautiful proof by third theorem. Milner's book. OK， 那为什么我们考虑这个 y 微分 y 微分或微分形式因为微分形式的 一个核心总值就是下列是微分形式用来就是计分的。So on Rn 上，我们考虑这样的integral。Okay. So on Rn, so 积分，你们积分的课已经学过这样的积分，积分。但是我想，我们想的，如果我们用一个 n 维的游行，我想考虑这样的积分。So anyway, 流行上n 形式的积分，我们考虑 anyway n 形式的积分。So we would like to define this kind of integral. Okay? But the step is very easy. So we already know on Rn we can integrate like this way. Okay? We know how to integrate. But m, the manifold has this开复解 open cover. And each patch you have a map to Rn. And phi u and the u of phi of u is something like that. In Rn you have okay. Is it okay? You have Rn. On here you can do the integration. Rn we know how to do the integration. So therefore, at each patch we have the omega can be written like this way. In each local coordinate, so we can just erase d here. Omega can be written like this. Each patch you can just integrate like this. So what you need to do is just nicely repatch on the whole manifold. That's what you need to do to define this. To do that, we will use so-called partition of unity. Of the locally finite open cover. Partition of unity. So 这个是单位分解。单位分解，最关键的工具是单位分解。So overlap, the important thing is overlap region. So overlap region here. overlap region of the open covering. So overlap region. So here we can integrate even here. A differential form over even dispatch. There's a V and U here. U here, phi of B here. But there's an overlap region here. Here. So you would like to avoid the double counting of the integral of the differential form. Okay? So if you add this local patch, you have an integration of this one, and you integration of this this n form here, but then you just double count this one. You just integrate twice on this region. Okay? To avoid that, we introduce downway vector. So this is U, maybe B, and this is U. Okay, this is. I think I should use B for red. And then this is U. And this is the overlap region. This is the overlap. So we define this kind of function. This is a 1. We define this kind of function. Define this kind of function. It's very smooth, but if you add them up, the total is equal to 1. You understand what I mean? That's why it's called downway function. So here, U alpha is the open covering, is chi fu, yeah, open covering. And chi alpha, each open patch, you have some function chi alpha. So this is chi B, this is chi U. But if you sum all the alpha, this should be always equal to 1. So this overlap region, chi B plus chi U should be equal to 1 on this purple, on this here. Okay. In total is equal to 1. So then, if you multiply this function, you don't need to do the overcounting on this overlapping region, because in total it becomes 1. It becomes 1. Okay. So therefore, and then you just have a chi alpha or omega. It's just a phi of U. Like this. If you define so each patch, you can define the integration of Rn like this one, and you just need to sum them up to define this quantity. So this is just sum of alpha, chi alpha, omega. So chi alpha is the chi alpha is this downway function. So then you can avoid overlapping, the double counting of overlapping region like this. And this locally finite open covering is at the, it's very simple. So at each point, you have only finite many open covering. Finite many open covering. So you cannot have like at each point, like there's an infinite many open covering if you have like this way. So the sum of alpha becomes infinite sum. Infinite sum. So that this is not well defined. So only at each point only finite many cover. Like in this case, only three open patch. Then sum is just three functions. So it's easy to define. It's easy to define. But if you have infinite many open coverings for each point, this 单位分解不能定义，不能定义单位分解。No, actually, so this locally finite open covering is no need to be compact.
Finite over cover.
So if it is compact, you can, of course, you can find only like a finite many open cover. But this locally finite open cover means that at the locally means that each point you only have a finite cover. But it can have infinite many open cover. But yeah. Okay, I think it's a good point to stop. Let's stop here. Now, unfortunately, I missed first half of the recording. 这个在 I course 有这个录像。不是李伟芬，离岛是，哦，离岛是，
主要是relative translated to
二导数，
微分那个differential。
哦 ，OK，Thank you very much。不好意思，离岛数，
但是 actually almost the same。
OK。Okay. Derivatives is true.
This is translated to differential is transformation.
Okay. Okay. Thank you very much.
元気元気元気元気よ。かわいい。しゃべらないの？大树，是大树。